I need to click. All right, great. So this is an awesome turnout. Thank you all for coming. I'm very happy to kind of make this highly interactive. Feel free to stop for questions. Don't worry about wearing. The undergrads will have to deal with it. I'm going to talk today about a line of work and kind of focus on some techniques that we've developed over a couple of papers with several collaborators, kind of designing algorithms for statistical, for learning tasks, learning simple statistics under differential privacy, and a new set of techniques for giving stronger guarantees. I know everybody's not caught up, or maybe everybody doesn't love privacy as much as I do. Shame. So I want to kind of motivate about why is privacy something that's worth working on. So one of the examples that's most striking to me is so every 10 years, the United States Census Bureau conducts a census. They try and ask everybody who's in the United States basic questions about where they live, who's in your house, this kind of stuff. Age, race, gender. And they release, from this huge data set, they release like billions of counting queries, who lives here, how many people. And in 2023, work by Aboud et al. Showed how to kind of take older techniques from the literature and apply them practically to turn these aggregate statistics into actual accurate answers. Reconstructing people's answers on the census for almost 100 million Americans, exactly getting their age bucket and sex and gender and such. Kind of a complete breakdown of privacy. And of course, it's not just a problem in statistics. Things like language models and fusion models certainly memorize huge amounts of details about the training data. Work from Nasser et al. Shows how you can extract training data from a lot of language models. Here's one that they got from ChatGPT. The overpopulation of deer in my area made everything on the plant list an appetizer. It goes on to list things. And if you Google this, it's a comment that Barbara made on mikesbackyardnursery.com in 2017, word for word, exactly. It's not clear why, our artificial general intelligence needs to memorize this string, but it has. So these are huge breaches of privacy, and we'd like to stop them. But I want to also emphasize that we need rigorous ways to reason about privacy. So in both of these cases, the system designers wanted to prevent exactly these breaches of privacy. They knew about these concerns. They came up with ad hoc techniques to stop these leakages. And later, researchers using sophisticated attacks were able to bypass their kind of ad hoc privacy protections. And so that's why we're going to turn to formal notions of privacy, try and formalize and prove that our systems preserve privacy. So to do that, we'll turn to the framework of differential privacy, which was proposed in 2006 and formalizes the idea that the outcomes of our analysis should not depend too much on any one person's data. Formally, we'll say that an algorithm is differentially private if for any two data sets that differ in one person's data, the output of the algorithm on those two data sets is indistinguishable in a certain sense. What this means is if we take any two data sets consisting of, we've got a bunch of people and then we change out one person for somebody else. We run the following thought experiment and we say that kind of no observer, when they see the output of the analysis, can tell whether they have, the data set or the orange data set. They can't reliably distinguish them. Okay, the formal definition of what I mean by this indistinguishability is here. It's not going to be too important in this talk, but I kind of want to put it out here for completeness. Our notion of indistinguishability is usually controlled by two parameters, epsilon and delta. And we say that two distributions are indistinguishable in this sense if for any event, the probability they assign to that event varies by at most a small kind of multiplicative factor like 1 plus epsilon, and a small additive factor delta, which is like something really, really small, the probability of like catastrophic failure. Okay, we don't need to remember that definition. So there are a great many techniques to ensure that our algorithms have this property, that they are indistinguishable in this sense. The key tool, the kind of foundational tool just for this talk, is to introduce Gaussian noise somewhere in your algorithm and then prove that it works out. So the basic idea here is that if I gave you a sample from either the blue distribution or the orange distribution, you wouldn't be able to tell which was which reliably. You wouldn't be able to kind of figure out with high probability which one it was. Okay, so in this talk, we're going to talk about basic statistics, very simple statistical tasks. The first is on just mean estimation. If I give you samples from the Gaussian, can you estimate the mean? Covariance estimation, samples from a Gaussian, can I estimate the covariance? And the thing that we'll actually kind of focus the most on is linear regression. Given samples from a kind of like a well-specified random design linear model, can you recover the true parameter? I'm going to kind of focus on, in this talk, I'm going to focus on the results for linear regression. And then, but talk about the meat of the talk, the technical bulk, will be on a kind of key subroutine that underlies our work, our results and improvements on all of these tasks under differential privacy. And then kind of time permitting, we'll talk a bit more about some related work and future directions. Okay. So I know this is a bad audience to do this in front of. I'm going to play fast and loose with the difference between linear regression and least squares. Okay, so here's our least squares or linear regression task. We're given a set of inputs X and labels Y, covariates and labels, and we want to output a vector in D dimensions that has low squared error. We want to have a squared error close to that of the OLS solution. Okay, we all know and love ordinary least squares. Now, of course, we'd like to just output the OLS solution. We can't do this because it breaks privacy. The output of the OLS solution itself is highly sensitive to changing any single data. Now, this objective we have kind of enforces a geometry on the problem. If I look at the quality of my solution, I kind of have the following picture, where as I move farther away from the OLS solution, my excess error goes up. But importantly, the geometry of this problem, of this optimization problem, depends heavily on the data. So if I move in some directions, my loss goes up very quickly. If I move in others, my loss moves very slowly. And this is kind of almost a traditional stumbling point for differentially private algorithms. But what we want to do, and like to kind of see this, is we want to minimize the excess error. And if we do some expanding and rearranging, we see that our excess error over the OLS solution is exactly some kind of norm where it's like our solution minus the OLS solution, but I've rescaled by this empirical covariance, what I'll call the empirical covariance here. And so in this problem, I want to, I'll save that point. Okay, let's talk about prior techniques for regression and for private regression and kind of the bottlenecks that they run into. Okay, I'll mention that linear regression is, almost the first thing you start solving once you invent differential privacy. So there are a lot of papers on this. I'm just going to get a sampling of them. A key technique is what's called sufficient statistics perturbation. I compute my sufficient statistics for the problem. I produce noisy versions of each of them, and then I combine them to produce an OLS solution. In some worst case sense, this is kind of minimax. People have proved that this is minimax optimal for some problems. But the issue is that I'm privately estimating the covariance of my data. And it turns out that this is actually a significantly harder problem than solving the regression problem. And so the number of samples I need grows at least with d to the 3/2. This is like a polynomial overhead over what I'd like. I'd like to get a good solution when I have only roughly d samples, matching the non-private setting. So these algorithms are often very practical, but theoretically, we're kind of dissatisfied with them. Another approach that can be practical in low dimensions is called subsample and aggregate, where I take my whole data set and I split it up into a bunch of chunks. I solve the OLS solution on each chunk, and then I kind of privately combine those estimates and output a good estimate at the end. And the way that this allows me, the key feature here is that because changing one data point here can only change one estimate. And so my overall sensitivity of this estimate may be kind of bounded. But this approach needs at least like order of d batches to do the private combination step, and needs order of d samples in each batch to get a good non-private estimate in the batch. And so this needs d squared examples. So we're dissatisfied with it. The next approach, the next class of approaches is through optimization. Okay? Least squares is a strongly convex loss. Differential privacy has a long, well-established line of work on private optimization, and we know how to solve these problems. Off-the-shelf tools, kind of applying existing techniques, run into a similar d to the 3/2 barrier. And recent, kind of regression-specific analyses get slightly better dependence on the dimension, but these are first-order methods. And so they're going to suffer on poorly conditioned problems. These first-order methods suffer on poorly conditioned problems. And so the number of samples they require grows with the condition number of the problem, which is we'd really like to avoid.
So what is K here?
K is the I don't have the definition. The ratio between the max and the minimum eigenvalue of X transpose X.
Okay, so basically K should be kappa.
Yeah.
I'll teach you how to write this.
Yeah. Kappa, yes. And there should be a little bubble that explains what it defines it.
So can I ask?
Yeah.
So can you explain what is this lower bound of d to the 3/2 for covariance estimation? This is with respect to what DP model and with respect to what norm, right? The covariance.
Yes. So central differential privacy. Sorry, I'm gonna. Get something to drink here. So the model is kind of the central approximate differential privacy.
So epsilon delta.
Mm-hmm.
And covariance estimation in which norm?
Spectral norm. So if I want to produce an estimate, sigma hat, such that I got if I want to produce a good spectral approximation to the true covariance, I need, focusing on the dimension, d to the 3/2 examples.
And this is like for epsilon delta and alpha to be constant.
Yeah. requiring, if I want to estimate in a stronger notion like Frobenius norm, then I need more samples, d squared. If I have time, I'll talk about.
This seems a little bit counterintuitive, right? Because even the outlier robust version of this can be done with examples, like.
Right, even information theoretically, it's a different story from robustness, right?
Okay, fantastic. And this depends on condition number. So basically, you're saying that your thing, because it uses the structure of linear regression, does not have a dependence on condition number in the sample complexity at all?
Our approach does not have a dependence on the condition number. These approaches that use first-order methods, all known approaches that kind of follow this private optimization blueprint, do depend on the condition number.
So even using like strong convexity and whatnot, you cannot remove it for your information. Okay.
Yeah, that I know how to do. I don't have a general lower bound for that kind of thing, but all known approaches, yeah. And then the fourth kind of class of approach, or okay, it's really one paper, work of Liu, Kong, and O, shows how to kind of really nail the sample complexity, get it exactly right in exponential time. And the idea is that they're working off of some robust statistic about the based on the over the parameter. You can kind of, we don't need to get into the details, but it involves maximizing over all directions in to find outliers and make sure that our output is robust and private.
Yeah, this is called regression depth.
Is this exactly I think I might be lying here. Yeah, it's something very similar, if not exactly. Yeah. Okay, so kind of all prior approaches to this work on our work on least squares requires either d to the 3/2 examples, a dependence on the condition number, or exponential time. And our approach avoids all three of these obstacles. Let's work with collaborators that appeared in Colt 2024. We call our algorithm insufficient statistics perturbation. It's epsilon delta differentially private. Asymptotically, it runs as fast as ordinary pairs. There's only a few parts of the algorithm that are kind of heavyweight, and it asymptotically matches OLS. And okay, we want the accuracy guarantee. On data that comes from a Gaussian random design with high probability, we get an estimate that has low excess error, where we get it like a 1 plus alpha approximation, where alpha is roughly something that depends on our privacy parameters, and then the dimension squared over the number of samples squared. So, okay, just for concreteness, here's what I mean by Gaussian random design. The covariates come from some multivariate Gaussian, and the labels are drawn from some well-specified model with IID noise. And to kind of digest this, the key thing to note is that to make alpha small, it suffices to take the number of samples roughly on the order of the dimension. In fact, this is the optimal dependence on d squared, and on d, n, and epsilon, and kind of close to optimal on the log if you care about that. But kind of crucially, our accuracy guarantee doesn't depend on the geometry of the problem. It doesn't depend on the true parameter or the true beta parameter or the covariance or the scale of the noise. The algorithm automatically adapts to these parameters.
So what do you mean by that? Like, what would be the alternative that, let's say, other weaker methods had?
Like a common approach in when you first learn privacy in a class, say my class next semester, you'll say like, assume all of these x's live in a ball of an L2 ball of radius r. And then maybe my error guarantee will grow with like log of R.
But this is something that you would only use for epsilon equals 0, right? Or for delta equals 0. Isn't like only the pure privacy setting that's of the.
That's in the pure privacy setting, you need this dependence. Yeah. I think like part of what's exciting about this work is being able to remove that dependence. It's not clear how to remove that dependence with epsilon, even if I give you epsilon delta.
Other question?
Yes.
You had n less than b, the least squares estimate wouldn't be very interesting in itself. So there's no real sacrifice there. And then my question though was, is alpha, is there some universal constant sitting out front of that?
Yeah. Yeah, it's bigger than I'd like to put on the slide.
Often that's true when it doesn't show up. Yeah.
Yeah. So
how do you, I mean, that's a bound, right? I mean,
yes.
Do you have any like idea of what it really is?
No, so it's bad news because that bound is what it really is.
I see.
So, the privacy, and I won't get in too much into it, but the privacy analysis of this algorithm is very complex, lots of lemmas. And, the rule of thumb is like every lemma, a factor of 2. So the number is not galactic, but it's maybe 500 or 1,000 or something. And what that means is because to ensure privacy, I need to add a lot of noise with large constants. So the kind of, the state of the art or the true story is this algorithm is very runnable. It's kind of simple to code up. But right now on most practical data sets, there will be another technique that's more accurate on. Yeah.
So even this wouldn't necessarily be too
precisely. Yeah. Until the data gets very big in some, maybe specific regime. But right, if I'm competing against, d to the 3 halves, I care a lot about that theoretically, but like the extra square root d is maybe not a huge penalty to pay practically. And I guess the other thing that really matters for practice is this guarantee. I've stated it for Gaussian data, but it actually kind of applies much more generally and relies only on the data being somewhat well concentrated. I'm not really using the Gaussian assumption. Cool. Other questions on the statement before I move on? Great. So I'm going to kind of now transition from talking about privacy to really just talking about what stability guarantees we need from our algorithm and how we can get those properties. So if you just look at this picture and you've taken, you've seen a one paper on privacy, something you might think to do is to compute the OLS solution and add Gaussian noise that's scaled to the inverse covariance of the data. This will mean that the noise we add matches the geometry of the problem. And I don't know, it's Gaussian noise. I already told you that Gaussian noise is useful, so it's maybe a kind of a useful starting point. However, this algorithm is kind of not private. It's dramatically not private for simple reasons. There exist adjacent data sets, X and Y, X, Y, and X prime, Y prime. Data sets that differ in one entry, but their OLS solutions are very different. Their covariances are very different. And so the output distributions might look like this. If I give you a sample from the blue one or the orange one, you can reliably tell which one it's from. So the output distributions are very, very highly distinguishable. This approach is not private. What our work is going to do is we come up with new non-private estimators that are stable in some sense. So we have a stable covariance estimate and a stable least squares estimate. And we also have one that we use for mean estimation. And then we run this algorithm with our stable estimators in place of the thing that we would like to do. And what this stability is going to ensure is that for any two input data sets, the output distribution is close. The output parameters are close. That means the output distribution is close. So, for the kind of bulk of the talk, we're just going to talk about what the stability notions we need are, and how we can achieve it. Okay.
But I just want to make sure you're saying, so the noise that you're adding has covariance at the invert of the noise of the original problem. And is that what you're indicating here with the empirical inverse of the empirical covariance as your covariance? I'm just trying to understand why the inverse, or
it's like
you're putting more noise in direction.
It's kind of the proper thing to do. So I didn't write that out, but I guess if I'm thinking fixed design random regression, then my
falls to outside there.
I can write on these. Brilliant.
Yeah.
Now, great. So in fixed design without privacy, then I have my beta OLS estimate.
Oh, okay. Sorry. Yeah. So that's going to have a certain covariance.
And then this is 1/n.
Yeah. Yeah.
Right?
Yeah. Okay. So you're just kind of matching that.
Yeah.
I see. Okay.
So that's the justification for why, this noise, this is exactly that noise, the same shape of the noise. It's reasonable to think then that if I could do this, I would be able to reason about the accuracy of these algorithms.
And what can you just say? Why not just a completely isotropic Gaussian noise, like what goes on there?
Yeah. So that hits my condition number problem. So if I add isotropic noise, I kind of need to add a lot of noise in the kind of the big directions.
Right.
Because to cover up changes in the parameter.
Gotcha.
But then that adds a lot of noise in the small directions. And therefore my loss grows very quickly. And how much is exactly the condition number, or the square root of the condition number. Yeah.
To understand this, like you're trying to imitate the original least squares by just adding the same directionality of geometry. The same geometry as original least squares.
Yes.
Probably that would give OLS solution.
Mm-hmm.
And then can you just comment on the stability? Why stability as a criterion? Or maybe we'll talk about it later.
No, this is just as good a place to talk about. Yeah. So these empirical estimates are highly unstable. And so if I change one point, I can move my parameters actually arbitrarily far.
Mm-hmm.
And so I need somehow to ensure that if I change one point, I can't move it very far. And so my distributions will over-effect for that. And so that's a stability condition on how much changing something. It's kind of like a Lipschitz condition. How much changing one thing here can change the output here. Okay, cool. So let's dig into this stability and kind of the key analysis. So I'm going to focus on producing this stable estimate of the covariance. And this is, as we've kind of seen, it's the important thing. I want to approximate the geometry of the problem so that I can add noise that matches the geometry. And a key quantity here is the leverage score of my data points. So the leverage of a point is the kind of exactly controls how much the covariance changes when I remove that point. It's a classical notion in statistics and regression analysis. If something has high leverage, it's highly influential. So what we're going to do to produce this stable estimator is we're going to have a leverage filtering subroutine. I'm going to look at my data. I'm going to throw out all the high leverage points. And once I do that, then I'll be left with a stable estimate. If my data doesn't have any high leverage points, then changing one point can't change the covariance too much. Formally, I'm going to kind of produce a filtering algorithm that takes in a data set and produces weights over the data set. So I'll allow it to produce a vector over weights. If I had 0, 1 outputs, then that means like either hard removal or inclusion in the data. I'll allow kind of soft removal to smooth things out. And I want 3 guarantees on my algorithm that will kind of work through over the next few minutes. First, I want something that I'll call soundness. I want the things that I assign weight to should in fact be inliers. They should have modest leverage scores. The next is completeness. When I run my filtering algorithm on something that has no outliers, then output weights will be the all ones vector. It's kind of I do a no-op on data that's actually clean. This will mean that when I run the algorithm, when I run my stable algorithm, I'm actually just running my ideal algorithm because I'm using the empirical OLS solution, using the empirical covariance.
So what's your definition of outlier? Like large leverage score?
High leverage score, yeah.
How high?
So I want, typically in typical data, we want leverage scores to be like D over N for typical Gaussian or sub-Gaussian data. So something, and we'll set that it's a user supply parameter, but something like D over N is the idea. The dimension over the number of samples.
So all of this is because like you're looking for like worst case times. Like the physical performance is going to be true only for Gaussian axis, but the privacy performance has to be true always.
Precisely.
Therefore, you have to do this tweaking.
Yeah. So in fact, this is a good point to bring up, which is the privacy guarantee, the worst case guarantee. I need, for any 2 data sets, no matter what they look like, I need to provide indistinguishability. If I was willing to cheat, I would say, look, on data that comes from a well-specified linear model, the OLS parameter is in fact usually stable. If I change 1 point on typical data, the parameters don't change too much. Therefore, my ideal algorithm will work. So it's clear to see why this method will be accurate, and it's clear to see clear as in not worth writing a paper about. Clear to see that on data that actually comes from this distribution, the ideal algorithm works. The kind of trick is like on any 2 worst case data sets, I need to provide these guarantees, no matter what they look like. And the key interesting guarantee for my stability, for my filtering algorithm is that it needs to be stable. For any 2 input data sets, I'm going to produce a weighting that is close in L1 distance. So what this means is like morally, I put in 2 data sets that differed on 1 point, and I get something out that looks a probability distribution that kind of morally differs on constant number of points. So this kind of stability means that my weights don't blow up too much. Okay. I claim kind of without
question online. Can you hear me?
Yeah, please.
Hey, this is Jerry. Just wonder if Y01 here, like W is a vector of length n. So, like as n grows, but you still just want constant, is that like too strict?
No, it's okay. So good question. I could, if you gave me an algorithm that had worse stability guarantees, I could give you a kind of less accurate algorithm. I want O of 1 because that matches the guarantees for like data sets that differ in 1 point.
Oh.
So if I have 2 data sets, they differ in 1 point, that's like the L1 distance of 1 in this scaling.
Okay, thanks.
And so somehow I kind of, if the weights had larger L1 distance, that would be kind of like blowing up the stability in some sense. Yeah. Okay, so yeah, so I kind of I claim without proof that if I can produce this subroutine for leverage scores, then that will give me a stable estimate of the covariance, which will, get me most of the way to the key result. So we're going to spend the rest of the time talking about how we can remove leverage filtering, how we can remove high leverage points from our data. Okay, so this is our definition of leverage score. And in one dimension, it's very simple. It's just the square of my point divided by the sum of squares. This thing on the bottom, I'll just, abuse notation, call it the covariance or the variance. Morally good enough for me. And right, so as we kind of said, we're aiming to remove points that have leverage much higher than d over n. This is the kind of standard threshold, and it's what works for Gaussian data. Okay, so why isn't this trivial? Why can't I just look at my data, compute the leverage scores? I've got a formula, throw out points that are too big. Here's the issue. Suppose I've got one data set where all the points are evenly split between +1 and -1. So here, all my points have leverage score 1 over n. This is, because d is 1, this is like exactly what I'm looking for. Great, this is like a perfect data set. However, if I take 1 point and I set it to 0, I change 1 point, now all the leverage scores are 1 over n minus 1. And so if I had set my leverage threshold at exactly 1 over n, I would say this data set on the top is perfect, no outliers. And I would say this data set on the bottom is completely full of outliers. Oh no, my life is ruined. So if I have a single fixed leverage threshold, this kind of outlier removal process is highly unstable. The good news is that this is in some sense the worst case. I can have many of the leverage scores can all grow, but it only went from 1 over n to 1 over n minus 1. And that's what's going to kind of save us. Okay, so I'll now, to kind of finish up, I'll introduce this leverage filtering algorithm and the kind of the keys to the analysis. Okay, in essentially complete detail, here's the leverage filtering. I take in a data set. I take in a leverage threshold that's a user-supplied parameter and some additional counting parameter k that is just a number, like 100 for us. And then I iterate over k's, and for each one, I do greedy leverage filtering on my data set, and then I have some slightly different leverage parameter. This is like my initial parameter times e to the j low, which is a joke. So I find, okay, I'll say what this leverage filtering is, but then I then compute weights for my data points. If you appeared in, sorry, I'm doing this in the wrong order. Here's the greedy leverage filtering algorithm. It's the first thing any of you would think of if I asked you to fill in this subroutine. I just start with all my points being active. I compute my leverage scores. I throw out points with high leverage score, and then either everything is thrown out, or I return a set of bounded leverage. Okay, so this is greedy leverage filtering. And so I run this subroutine on my data at a bunch of different subsets, at a bunch of different outlier thresholds. And then I weight my points depending on how many subsets they got into. So if you were in all the subsets, then you get a weight of 1. If you were in none of them, you get a weight of 0, and then smoothly in between that. Okay, I have to find some notation. The leverage score on a subset is exactly what you think it is. Does this, syntactically make sense? Cool. So what's going on here is, suppose I've got my data set of points 1 through n. Initially, everything is in my good subset. And then I find a series of subsets. So when K is large, my outlier parameter is big. And maybe all of my points but one are an inlier. And then I start shrinking the outlier threshold slightly. And as I go down, maybe I remove more and more points. Until I'm all the way at my smallest threshold, I find my smallest subset. And then I assign weights based kind of just by looking at this matrix. This one was in all the sets, it gets 0.1. This one was in only one split subset. And so it gets weight 1 over K. Okay. So let's look back at our 3 goals. The soundness should be clear. The only way a point gets weight is if it survived at least one of the greedy thresholding. So if I have a mega outlier, it'll always get 0 weight. Completeness is also clear because if I have data, if greedy thresholding removes nothing, I assign weight 1 to everything. And then now we need to talk about stability, which is the hard part. Okay. We're going to walk through a few of the dilemmas. We'll kind of prove them to varying degrees, to leading to the conclusion that the weights we produce are in fact stable.
So can I ask?
Yeah.
But where does this come from? Like, is there like a well-defined optimization problem that you were able to solve? Would get that with this an algorithm to solve this problem? Like,
that's a really good question. Yeah. I don't know. Part of the reason I chew through this is to try and try and find a simple optimization problem. The analysis here is kind of very strange. It's like very sensitive and very focused on covariance estimation. But I don't know how to cleanly, I don't know a version of this algorithm that is like solve this optimization problem, output the weights, and then you're good. That's kind of the question you're asking.
Yes.
Yeah. I don't know that. It seems like one should exist, but yeah. Some of the simple versions of optimization problems clearly fail, but maybe there's some other way to view it. Okay, so let's look at this. Okay, so let's prove this first lemma. Well, I've already been using it informally. We'll call a subset S an L good subset if all the leverage scores are bounded by L. So I take my data, I've got some subset, I compute the covariance, and if everything's inside the green line, then this is a good subset. This picture is like some ellipse of the corresponding to the leverage scores being bounded by L. If I take, a different subset, I get a different ellipse, but some of the points are outside the subset, and so this is not an L good subset. Okay. Our lemma is that, the first lemma we need to prove is, fix any data set, fix any leverage threshold. If I have, the lemma says, if I have an L good subset in my data, that subset, if I have a good subset T in my data, it shows up in the output of greedy filtering. If anybody has seen a lemma like this before, I'd be very interested to know. It's quite simple. We'll prove it right now. A quick corollary is that greedy leverage filtering for any data set and any leverage threshold finds the unique largest L good subset. There's always a well-defined unique largest subset that contains everything else. Okay. The quick proof is that this greedy filtering thing only removes, rank 1 elements from the covariance And the leverage is non-decreasing under removal. I've got okay, the complete proof is like, write out the Sherman-Morrison formula. And if I fix a good subset in any larger subset, the point is always has nothing in that good subset ever gets removed. So this is kind of our first step about where we need to reason about the greedy leverage filtering routine. In fact, we don't need such a strong property for other approaches, but it makes things nice to prove. The next step is that, okay, I will just state this lemma, which says that if you remove something from a good subset, then the resulting thing is still pretty good. This is like what we saw in that first example. If I have something where all the leverages are bounded and I drop a point, the leverages can't grow too much. And then the next thing that we need to prove is to reason about what this looks like on adjacent data sets. So I have two data sets. I take one data set and I compute my kind of families of all these good subsets. And I compute on an adjacent data set another family of all the good subsets. And I want to reason about how these things are related. And what this says is that, where's my nice picture? Okay, I'm going to skip to where we use this previous lemma in the interest of time. So what we actually end up proving is I have two data sets. I compute my families of good subsets here. And here are my leverage thresholds. I found a good subset at leverage threshold 1, another at leverage threshold 2, all the way on up. And I found a kind of increasing family of subsets on that data set. And similarly, on X prime, I found some other family of good subsets. And what we prove is a kind of like intertwining of these subsets. Because if I remove a point, the point that differs, that subset is a good subset on my other data set. Which means that this subset, the thing I find here, has to show up in here, in form, almost complete, like up to small details. This subset shows up in this subset, and this one shows up in here, and this one shows up in here, all the way on up, and of course on the other ways. And so we kind of have this phenomenon where for any fixed threshold, the greedy algorithm can be very unstable because changing one point can move lots of points across the threshold. But by looking at a larger number of thresholds, we can kind of stabilize the greedy algorithm and show that on average, the subsets are very similar, which leads to the weights being stable. Okay, so yeah, in the interest of time, I want to kind of move on to wrap up. Okay, so let's kind of summarize this technical portion of the talk. We saw this leverage filtering routine, which gives us a stable covariance estimate. And we talked about, the kind of stability guarantees we need, the guarantees that we need out of it, which allow us to plug into the private algorithm. So this routine is just for covariance estimation, but it's actually the same thing for mean estimation and for linear regression. And all you need to do is to extend this approach is swap in a different greedy algorithm and then prove a bunch of different lemmas about that greedy algorithm. Okay, all you need to do. But it's this same story applies in several different places. And yeah, so in our work in these papers, we've used it for new results in mean estimation, covariance estimation, and linear regression. I want to kind of just conclude by talking very briefly about a couple different topics outside of privacy that are related to these notions. The first is to kind of compare with the literature on fast approximate linear system solving. So this is a classic, classic problem in computer science and applied math and all over. Where I want to solve least squares, I want to solve it more efficiently than computing the exact solution. And in particular, people study it where the number of samples is much, much bigger than the dimension. How can I solve this efficiently? And in a lot of these approaches, leverage scores play a key role. What they're trying to do, what many of these papers try to do, is find a small subset of the data points where the solution on that subset looks like the true solution. However, it's kind of what's going on in these papers is almost exactly the opposite of what we're trying to do in this privacy regime. Because in these papers, you want to retain the high leverage points because they are very highly influential on your solution. Well, we want to toss out we want to toss the high leverage points. In fact, we have to, because if the solution is unstable on data points that have high leverage. So it's interesting that kind of the mathematical tools underlying them are very similar, but they're operating in quite different regimes. And I also just want to mention very briefly another kind of recent line of work. Obviously, robust statistics has been studied for a long time, but a new version of or new type of question in robustness was either invented or hit upon by work and repopularized by Broderick, Giordano, and Meager in 2020. And they kind of, in this paper, they asked this question like, are my conclusions robust to dropping a few samples from the data? And in particular, they work in this setup where you run your OLS on some data set and say you're interested in the coefficient for the first problem. And you're interested in this like first coefficient, which is the effect you're trying to estimate. And suppose you observe that it's significant and positive. You want to ask the question, can I remove a small fraction of points such that my effect drops to zero or drops to negative? So in this paper, they find that a huge number of pretty important economics papers, you can drop like 1% of the data and flip the effects the other way. Very strong non-robustness. And there are a number of the work in their paper was algorithms and kind of heuristic analysis in defining this problem. And there are a number of follow-up papers, which I thought I had citations to, but follow-up papers proving these, giving provable guarantees for this type of problem. And it's actually very similar to what we were the tools that we were working on here, where we're asking, like, are there influential points? And if there are influential points, can I guarantee that I've removed them from from my data set? And these types of guarantees that we need to prove privacy are very similar, at least have a very similar flavor to the types of guarantees that are used in these regression auditing problems.
Gavin, can I ask a question here?
Yeah.
Like here, like it sounds like if I'm the adversary and I want to find the best points to remove to drive beta 1 to negative, I would have to consider the labels as well, in addition to just the leverage.
Yeah, that's true. So what I haven't yes, absolutely, because high residual points are also highly influential. the techniques that we develop for our linear regression solution give a stable residual filtering subroutine as well. And that kind of follows the same blueprints, but has more complicated lemmas. And these are exactly the kinds of calculations that show up when we're thinking about influence functions for regression and how does dropping a point change my regression estimate.
All right, thank you.
Yeah. Okay, yeah, and then finally, just a couple future directions. One is, as we talked about, practical constants. So yeah, I think it's like the error of OLS plus 500 times, my parameters. And if I have an algorithm with small constants that pays a factor of square root d, the data has to be fairly big before this algorithm is competitive. There is code online for some of the algorithms. And another natural direction is thinking about applying these frameworks to other tasks and trying to generalize them and understand what's really being used about the problem. These algorithms that we have here kind of respect the geometry of the problem without explicitly privately estimating it. One thing that I think is very interesting is how we can try and apply this to optimization. So the state of the art in private optimization is to compute the gradient of your data and add spherical Gaussian noise. You should believe that adding spherical Gaussian noise is really bad for accuracy because not all directions are equally important. But we don't have algorithms to really beat that in a strong way. So not that these techniques exactly will, not that I expect these techniques directly to improve private optimization, but that this kind of mode of thinking about the problem, I think will be fruitful. So with that, thank you very much for your attention and great questions. Yeah.
So I'm getting back to your lady with the deer in the backyard.
Yeah.
How on earth does this help protect privacy?
If I stop, I want to stop ChatGPT from remembering, individuals' comments.
If that's what it does, interesting. I mean, how can you know which ones have leverage?
Oh, okay. So yeah, these techniques may only indirectly be used for, at least, okay, right now they're not practical and I'm not going to use them to train a language model. But, things like mean estimation can be used for gradient descent. And so if I can train my model, and basically a point I'd be worried in this, the kind of to port it over, I'd be worried that maybe like a gradient of the model's weights with respect to a specific person's data set has high leverage, is highly influential. And I'd like to cover up that contribution of the gradient. Does that answer your question?
I think the way they do it, they don't know who it comes from.